Awesome. Doing great. That's good to hear. Let's see how people are doing on the Linux server. Hey, we got a few people logged in. That's good. Alright, so if you haven't already, go ahead and log into the Linux server. linux.engrcs.com, and we're going to mess around with that for a little bit. So once you're logged on, go ahead and run the answer program. Same thing that you've done in 224. If you're in 224, just at the command prompt, type the word answer and hit enter. And you should see something like this. So let's log on over there. So if you say answer, you should just get a window popping up that says waiting for a question from the teacher. Alright, so I'm going to post a question just as kind of a pulse check question, which says, let me know if you are here. And this should pop up on your window if you're running the answer command. Alright, we have our first winner. Cool. Alright, so I'm going to go ahead and play along myself and say, I am here too. Excellent. Alright, got 21 people. That's fantastic. That's almost the whole participant list. Let's see. Did you get my answer? Yes, I did. All right, awesomeness. Any questions from last time? Or any questions on the homework? I think we've gone through everything that you need to be able to do the homework. And I believe.
I have a question on like for first section in like specifically 1.12 where like it says list all elements of the following sets and like you have to find all the elements in P and like I'm not sure what P actually is.
So let's see, which question are you looking at? Which section and which question?
1.12C.
1.12C. Okay, so so that funny looking P, let me bring this over to my window here. So that funny looking P, I believe, is the set of all positive numbers. It doesn't tell you that anywhere, does it?
Right after that.
It does tell
Ah,
you.
we use the symbol P instead of writing 1, 2, 3, dot, dot, dot. So yeah, that's the set of positive integers.
Okay, thanks.
Yep.
Shouldn't that just be natural numbers too?
So the natural numbers in this book includes the number 0. That is not totally standardized, though. Some books use the natural numbers and the positives the same way. So I usually try to stay away from the word natural numbers, the term natural numbers, because there is some ambiguity there. All right. Other homework questions or questions on anything?
Yeah, Nick, I had a quick question.
Sure.
On the 1, 2 for number 4, when it's saying for like part A, when we have like the A subset of B, B subset of C, then A is subset of C, are we making our own like subsets to then like prove with, or?
Yeah. So 1.2 number 4 says give examples to illustrate the following facts. So we're not doing a proof here, okay? Because we can't prove by examples, but you're demonstrating a case where these things are true. So what you want to do is define your own sets A, B, and C. Okay, they have to come from this universe of numbers 1 through 9. So they have to be some sort of subset of that set U. But pick some interesting sets A, B, and C to illustrate that A is a subset of B, B is a subset of C, and also A is a subset of C. Okay, try to pick a set A and B such that A take away B is different from B take away A. And try to find interesting examples, right? For example, I could pick A, B, and C to all be the empty set, and then I could say, yeah, A is a subset of B, B is a subset of C, right? But that's not terribly interesting, right? Try to pick some sets that are different from each other, but for which this property is confirmed. So just play around with it.
Okay, cool. Thank you.
Yeah. Someone says my advice is to keep it simple. Yeah, especially when we're dealing with cross products. Don't make sets with 6 numbers in them because you're going to get into a lot of combinations. But make something with 2 elements in it maybe, and that should work pretty well. All right, so we have 29 people signed in, which is almost the entire class. We've got 21 people on the server running the answer command. So a few people still aren't doing that. If you don't know how to do that, or you're having difficulties, or you have not logged into the Linux server or something like that, come by office hours today at 2 and let's work out the details. Okay, and you can just sort of, we're not going to do anything critical. I just want to play around with this a little bit today, and I think the answer tool might help us with that. So let's post a different question here. All right, so I'm going to ask you to define a set A containing a few elements and just show me the contents of that set. So write something like, A equals curly bracket and what you want to have in that set. And it can be numbers or letters or words or anything else that you can type. And, 3 or 4 elements. Cool. Nice. All right, so you're going to be playing with set operations here. right. Yeah, tab and enter will get you the submit button. So will your mouse. You can actually click on it. Yep, good. Oh, really? That's interesting. So at least one person says their mouse doesn't work for clicking on that. Oh, okay, yeah, it could be on Macs. So tab and enter or tab and space will get you there. And it's faster than mousing anyway. All right, so second question. Go ahead and define a second set B that also contains a few elements. All right, we have some awesome sets too. All right, so go ahead and write down what the union of those two sets is now. And I meant for it to not be clearing out your old answers so you wouldn't have to remember what those sets are. But that may not be working. Yeah, it's supposed to, we're debugging the system here. All right, hold on a second here. All right, if you don't remember what the sets were, just go ahead and submit an empty answer. And let me try something else. This is the first class I've actually used the system in live, so we're doing a bit of debugging here. Oh, someone restarted Putty and it works now. That's good. For the union symbol, I just used a lowercase u and it actually kind of looks like a union. And yeah, you can use an N for intersection. That's a pretty good stand-in. All right, cool. Lots of good answers. Yeah, there's simple and then there's fun. All right, let me try this. All right, I'm going to tweak this code a little bit over the weekend. All right, cool. That's all the testing I'm gonna do on that for now. We'll dig this up again on Monday, and I'll make some improvements to it before then. But thank you. So that seemed to work, and it didn't seem to like crash the system or anything like that. So that's good to know. All right. So after you answer the current question, it should just tell you that the Q&A is over, and it should exit, and you're free to log out of the server if you want. We're good to move on from there. All right, so let's continue talking about set theory. So we were talking about set identities, right? Some of these things that look like stuff we did in Engineering 250. So A union B is equal to B union A. The complement of A union B is the complement of A intersect the complement of B, De Morgan's theorem, right? So we played with some of these set identities, and we ended up by talking about membership tables. And membership tables are really just truth tables. But we made a table and we said for any element in the universe, for any set, it's either in the set or it's not in the set. And we did something like this. Prove the complement of A union B is the complement of A intersect the complement of B. So we said, well, let's take a pair of sets A, B, and for any element in the universe, there's exactly 4 possibilities. It's not in either set, it's in B only, it's in A only, or it's in both A and B. And then we said we can make columns to define, for example, if an element that we're thinking of is in the union. And it turns out if the element is in B or A or both, it will also be in the union. And if it's in neither A nor B, it won't be in the union. And if something is not in a set, then it is in the complement. And if something is in a set, then it's not in the complement. And so we can define these membership tables for different expressions involving our sets. So someone asked, can we use membership tables in proofs? Only if I say use a membership table. Yeah, you can. If I don't want you to use a membership table, I'll say don't use a membership table. But in general, we can use this just like we would use a truth table. But you will see questions on tests sometimes where I'll say, prove this without using membership tables, and then you got to do it a different way. But in general, yeah, this is a totally valid way to prove something. It's not like finding an example that shows it's true. We're really proving that for anything that we pick, any set, right, these things are going to be equivalent. So this is exactly the truth table that you did when you proved De Morgan's theorem in Boolean algebra, right? If something's not in A, then it is in the complement. If something is in A, it's not in the complement. Similarly for B. And then we can define the intersection. Well, something is in the intersection of these two sets only if it's in both sets. So here, an element is in both A bar and B bar. It's going to be in their intersection. But if the element is not in the complement of B, it's not going to be in the intersection with the complement of B. So all of these will be zeros. And now we can make an observation, which is that this and this are exactly the same. Meaning that for any element we think of in the universe, it will be in this set, A union B bar, if and only if it's in this set, A bar intersect B bar. And it will not be in this set, if and only if it's not in that set. Definition of equality. So based on this, we can say absolutely these two sets are exactly the same. In the sense that if an element is here, it's also there, and if an element's there, it's also here. Right, so that's a membership table. And it's really just a truth table, right? If we change these to ors, and we change this to an and, We're back in Engineering 250. It's the same stuff. Alright, what else can we do? There's an example in the book that talks about families of sets. And let's play with this, because it's kind of surprising, maybe, what we get out of this. So let me define a family of sets. So let's define a family of sets. A sub I, where I is equal to 1, 2, 3, and so on. So I've defined an infinite number of sets now. I have a set A1, I have another set A2, I have another set A3. Here's what my sets look like. The set AI consists of the integers I plus 1, I plus 2, and so on. Forever. Somebody asked, how could we have proved that De Morgan's theorem without using a membership table? We can do it using some of the identities. De Morgan's is a little tricky to prove. It's a pretty low-level theorem. But if you can prove De Morgan's in Engineering 250, you can prove it in CSE215. We use identities, we use facts that we can, use commutativity and associativity, and we can distribute things and so on and so forth. Proving De Morgan's without a membership table or a truth table is actually tricky, because that's a really low-level one. But in general, if you're given an identity and you're asked to prove that it's true, a lot of times we can turn one of the expressions into another by doing things like distributing terms that we're ANDing, using De Morgan's theorem, things like that. We'll do a little bit of that, but we won't go terribly deep into that, because membership tables are such a quick, easy way to do these proofs. All right, so we have a family of sets here. So for example, the set A1 is just our positive integers. The set A2 is almost the same thing, but it starts with 2. The set A3 is a smaller set, it starts with 3. Right? There's also a set A1000, which is the positive integer starting from 1000. And so on. So an infinite family of sets, and each set is infinite. All right, so we can take the union of sets. We could say A1 union A2. We could also say A1 union A2 union A3. And we might want to also take the union with A4. Okay, we have a shorthand for writing something like this. We can say a union from I equals 1 to 4 of A sub I. Okay, we do summation symbols in math class. We can do something like a summation symbol with logic. So this is a shorthand which says let I go from 1 to 4. First let's take A1, and then let's union that with A2, and union that with A3, and union that with A4. So this is a shorthand. We can use it for whatever sets we have. We don't have to start from 1. We could do the union from 10 to 15, right? And keep in mind, this is basically a for loop, right? In C, we would write, for I equals 1, I less than or equal to 4, I plus plus. And we would do something with, A sub I. We would add it to a running union or something. So these summation symbols, these unions over ranges of integers, they're really just for loops. All right, what is the union of these four things? What do we get if we take A1 union A2, A3, and A4? What do we end up with? Somebody pop me on microphone or a chat. Bunch of people. We end up with A1. Right? That kind of makes sense, right? If I take A1 and I union it with A1000, well, everything from here is already in A1, because A1 eventually includes 1,000, 1,000, 1,002, and there's nothing missing from A1, right? So when I add anything to A1, I'm just going to end up with A1. All right, we can also define an intersection from I equals 1 to n of AI. And what is that going to leave me with? Well, let's look at A1 intersect A2 intersect A3 intersect A4. Just as an example, what is that going to be equal to? All right, lots of people saying A4. That is correct. So if I take the intersection, every time I intersect with some bigger A sub I, right, an A with a bigger subscript on it, I lose something. A1 intersect A2, I lose that 1. And I end up with just A2. And then if I intersect that with A3, I'm going to have exactly the same stuff, except I'm going to lose that 2 because it's not in A3. And when I intersect with A4, I'm going to lose the 3. I'm going to end up with just A4. So the intersection from 1 to n of AI is equal to AN. And the union from 1 to n of AI was just A1. All right, what about if I do the union from I equals 1 to infinity of AI? Now, what do we mean by infinity here? There's no set A sub infinity, right? The subscript has to be a positive integer. Infinity is not a positive integer. What this means is take the intersection of all of the AI. A1, A2, A3, A4, A million, A zillion, A 10 zillion, and 5. Every possible subset in this family of sets, every set in this family of sets, you want to take the union of all of them. It's an infinite union. So what do you end up with? One person already got it.
Still be A1.
It's still A1. Because no matter how many other things I add to this set, right, each of these things is still just a subset of A1. I'm just going to end up with A1. All right, well, you know where it's going now. What happens when I take the infinite intersection of these? What am I going to end up with? So one person said A infinity, and there is no A infinity, right? Because our A sub I has to be a positive integer, and infinity is not a positive integer. But that's the right idea. All right, so we got a few people who figured this out already. This is going to give you the empty set. It is defined, and we don't necessarily know that. One person said undefined question mark. It's not necessarily defined, but in this case we actually can find a definitive answer. That's not always guaranteed. But it turns out we can actually prove that this infinite intersection is the empty set. Okay, how do we know that the intersection is the empty set? Well, we can do a proof by contradiction. Suppose you come to me and you say, it's not the empty set. There is some element in that infinite intersection. Okay, I will turn to you and I'll say, give me, at least one element in that intersection. And you say, well, that intersection is going to have the number 17 in it. Okay, so it's not empty. Well, I can take that intersection and I can say, well, we can intersect that with A18, and A18 does not have 17 in it. And since 17 is missing from at least one of these things we're taking the intersection of, it can't be in the total intersection. And then you'll say, no, I meant 17,000. I think 17,000 is in that intersection. Well, our intersection includes the intersection with A17,001, which contains integers bigger than or equal to 17,001, does not contain 17,000. So that can't be in the intersection either. And any positive integer that you can think of, I can prove it's not in that intersection because there is a set A sub that number plus 1 that doesn't contain that number. And so the only possible conclusion is there is nothing in that intersection. The intersection is the empty set. And that's one of our first hints that something weird happens around infinities. Right? Because for a finite n, the intersection just gives us another member of our family of sets. But when we intersect everything, we find out that we have nothing. And that's a little bit weird. That's also another pathway to topology. That's a distinction between open and closed sets, is whether you can do infinite unions and intersections. Somebody said the magic words in chat, aleph, aleph, and aleph naught, and things like that. We're going to get to some more interesting consequences of infinity today. All right, so intersections and unions, we can do them, between two things, between three things. We can do them over a range of numbers, and we'll come back to that sometimes when we deal with sets. Not a whole lot. All right. Let's talk about representing sets on computers. So suppose I have a universe consisting of a few letters. Let's say our universe consists of the letters A, B, C, D, E. And I have some sets. So A is the set containing A, C, E. And B is the set containing D, E. And C is the set containing A, C. That's a different C from that one. All right, we have a computer. We want to somehow store these sets and this information about these sets and the universe and so on inside a computer. There's a really clever way we can do this. Now, to make this work, we need to actually think of the set as being ordered. So we have to think of our elements as being in this particular order. And we're still going to say, that this set is the same as that set. We're not going to change our mathematics. But when we take our set and we put it in the computer, we're going to think about our elements as being in a particular order. And what we're going to do is we're going to use a bit to represent the membership of each element in our set. We have 5 things in our universe. We're going to use 5 bits to represent each possible set. So our universe is going to be the number 11111. Our set A is going to be the number 10101. Okay, and again, we're thinking about this as each of these bits corresponds to a particular element of our set universe. So what binary number would represent the set B? 5-bit binary number. Cool. 0, 0, 0, 1, 1. Because it contains D and E, it does not contain A, B, and C. And our set C would be 1, 0, 1, 0, 0. All right, pretty simple conversion from a set to a binary number, right? We've got some really powerful machinery here all of a sudden. So first of all, suppose I want to take A union B. So I want to take A and B and put them together into a set. That's going to be the set A, C, D, E. In binary, that's going to be 1, 0, 1, 1, 1. Anybody have a theory for how we could get this binary number from these two binary numbers using some kind of logic operation?
You could OR them.
We could OR them. This is nothing but the logical OR of 1, 0, 1, 0, 1 and 0, 0, 0, 1, 1. 1, 1, 1, 0, 1. And our intersection, so let's do A intersect B. That's just the set E. Well, 1, 0, 1, 0, 1 ANDed with 0, 0, 0, 1, 1. There's a 1, 0, 0, 0, 0. And that's the binary representation for the set containing just E. So we can take the union of two sets by simply ORing their binary strings together. And we can take the intersection of two sets by simply ANDing their binary strings together. What if I want the complement of a set? What do you think I do? Yep, just do the negation, do the not operation. B is 0, 0, 0, 1, 1. B bar will be 1, 1, 1, 0, 0. And sure enough, what does this mean? B bar is a set A, B, C. And that is the complement of the set DE. So once we have our sets stored internally in these binary representations, it's really easy to do manipulations. How can we tell if two sets are the same? See if their binary representations are the same. Because D, comma, E gets written like this. E, comma, D also gets written like this. So we don't have to worry about order. Guaranteed, the bit strings for two sets will be the same if and only if those two sets are the same. All right, back to subsets. What does our entire universe look like? It's a string consisting of all ones. Any other 5-bit number that I write corresponds to some subset of the universe. Right? Because I write down a pattern of 5 ones and zeros, and wherever there's 1, I'm including that element. Where there's a 0, I'm not including it. That's a member of, you know, the collection of sets that have elements from that universe. Well, think about the power set of the universe. That's the collection of all subsets of the universe. Well, any subset corresponds to a 5-bit number, and any 5-bit number corresponds to a subset. And by the way, what set does that correspond to? Yeah, that's the good old empty set. And this set is the entire universe. All right, how many 5-bit numbers are there? 5 bits, 2 to the 5th possible numbers, 32. Every 5-bit number is a subset of the universe. There must be 32 subsets. So this is another way we can see our thing that we came up with the other day for a finite set. We said the cardinality of the power set of S is equal to 2 raised to the cardinality of S. This is another way to see that. Because if we take any set S, we can say, well, that's our entire universe. If it contains this many elements, then every subset can be represented as a string containing that many bits. And how many such bits strings can we make? 2 raised to that number. So that's how many subsets we have. So this is a useful tool for certainly coding programs that let us interact with sets, but also for theoretically thinking about some things like, how many things are in the subset, in the collection of subsets of a set. All right, so we'll play with that from time to time. Let's talk about functions. So we deal with functions in math classes, and we deal with functions in programming, right? Functions, subroutines. Let's look at more formally what functions are about. And they basically come from sets. So given two sets, A and B, we can define a function f. And this is basically an assignment or a mapping. It's an assignment of an element little b in the set B for each element of A. So we have a set A over here, we have a set B over here. A function is an assignment of an element from here for each element over there. So we write f is a function from A to B, terminology. So f is a function going from A to set B. And if an element A is assigned to element B, we write f of A equals B. And it means this association associates the element B with the element A. And we think of this pictorially sometimes with a set of bubbly looking shapes. And here's an element A and here's an element B. And we can draw an arrow and label that F. So F is taking this element to that element. And we can represent functions lots of ways. We can represent them in words. We can represent them in pictures. We can represent them as mathematical expressions like, f of x equals x squared. We can represent them with a computer program called square root that takes a double precision floating point number and returns the square root of it. So any function that we can think of corresponds to one of these associations, and any association like this corresponds to a function. So for example, suppose that A and B are the set of all integers, positive, negative, 0. And suppose that f of A is equal to 2 times a. Right? That's a perfectly fine function. For every element a in the set of integers, we've associated another element in the set of integers, which is twice the value of a. So f of 1 is equal to 2, f of negative 1 is equal to negative 2, f of 0 is equal to 0, and so on. All right, so more terminology. The thing that we're mapping from, this is called the domain of the function. The thing that we're mapping to is called the codomain of the function. When we have an element A and we map it to something, we can say that B is the image of A. So the image means the thing that F maps something to. We can also say A is the pre-image of B. We don't say that a lot, though. But we do talk about images. Someone says this reminds them of transformations from linear algebra. Very much the same thing. Right? That's an example of a function. Different domain and different codomain, but it still maps elements of that first set into elements of the second set. All right, another way we can represent, cool, awesome, helps you picture this, good. Another way we can represent functions is by simply showing for every element in A what it maps to. In other words, if I were to write out f of every value in A, I can completely define this function. I don't have to say f of A equals 2A. So I could write down a set of ordered pairs, for example, 0 maps to 0, 1 maps to 2, 2 maps to 4, 3 maps to 6, and negative 1 maps to minus 2, and negative 2 maps to minus 4, and so on. And if I listed all of those out for all possible values of A for all integers, that would perfectly define the function. And I wouldn't have to know anything about multiplication, right? If you wanted to know what f of 3 was equal to, you could just look in here and say, oh yeah, f of 3 is 6. So here again, we see sets of ordered tuples, and a collection of those ordered tuples could be sufficient to define a function. All right, so think about this now. If we have a function f, we can define it as the set of all A, comma, f of A, such that A is an element of the domain, right? This is a perfectly equivalent way of defining the function f. So f can be defined as f can be written as this. Well, have we seen tuples before? What were we talking about when we talked about ordered pairs?
The cross product.
The cross product. This thing here is a subset of A cross B. Any function that I can think of from integers to integers will end up being some subset of the cross product of z with itself. If I think of the function as this set of ordered pairs. So if I think about real valued functions, things that take numbers and give you back numbers, I can take any function, sine, cosine, 1 over x, square root of x, inverse hyperbolic cotangent of x, and I can write it as a set of ordered pairs. And that family of ordered pairs that I end up with is a subset of the cross product of the reals with itself. Which means if I take the power set of the reals crossed with itself, I have a set that contains every possible mathematical function of one variable. Any function I can think of, any function you can ever learn about in a math class, is contained in this set. Right? 6 characters. So this is part of why set theory is so foundational to mathematics. Because we can boil down so much advanced mathematics to just thinking about sets and set operations and characteristics of sets. All right. Now try to picture what you get when you take R and cross R, and then you take the power set of that. That's pretty freaky. And a lot of things in this set will not be a function. But let's think about this a different way. So we looked at taking cross products of intervals, and we got rectangles, right? If we take the cross product of all of R with all of R, what do we get? We get the whole real plane. All right, so this part right here, that's just the whole real plane. It's all the xy points. Now what happens if I take a subset of that? Well, I can get all kinds of subsets, but sometimes when I take a subset, what am I going to get? I'm going to get some kind of curve. Well, that subset happens to correspond to some kind of phase-shifted sine wave. Right? That's the sense in which any function that we can think of will be somewhere in this power set. Because any function that we can think of mathematically from reals to reals is just some kind of curve on this real plane. I cheated. That's not a function anymore. Right? And any curve is just a collection of points from this plane. Collection of points, that's going to be a subset of the real plane. All right, so sets are foundational. All right. Let's take a 5-minute break, and then we're going to come back and we're going to shift gears. But let's take a break for about 5 minutes. We'll come back and we'll talk a little bit more about functions on Monday, because I want to talk about classes of functions. I want to talk about injectiveness, surjectiveness, and bijectiveness. But that's kind of a bit of a sidebar, and it's fairly confusing, and I don't want to do that on a Friday. So let's stretch our brains for about 5 minutes. We'll come back and we're going to talk about very large sets and the notion of infinity. All right. So I'm going to get a drink of water, and I'll be back in a few minutes. let's see, someone asked, are we going to set up coding for functions later? I mean, we certainly do in the other CS courses, and we will be doing some coding in this class. I don't know if we're going to do coding specifically around this idea of functions. We might. I haven't figured out what the coding assignments will be, but we'll have a couple of programs to write during the course. And they might tie back into functions. All right, so we're back from break now. So one of the reasons that we introduced functions when talking about sets is that we can use functions to discuss the size or cardinality of sets. All right, so we defined for a finite set. Remember, a finite set is a set containing a finite number of things. So a million things, it's still a finite set. So for a finite set S, the cardinality of S, which we write as absolute value, this is just the number of elements in S. And cardinality for finite sets is just an integer. 0, 1, 2, 3, a million, whatever. But for infinite sets, cardinality is very different. Because when we want to talk about the cardinality of, say, the set of all integers, well, there's no number that corresponds to that. Right? It's bigger than a million, it's bigger than a billion, it's bigger than a trillion. Infinity is not a number, so we can't say this is infinity. So how do we describe the size of the set of real numbers? Well, it turns out that even if we don't know how to describe the size of this, we can compare cardinalities as follows. So definition for any two sets, A and B, and these do not have to be finite. These two sets have the same size, the same cardinality, if and only if. So this is our abbreviation for if and only if, just IFF. If and only if there is a one-to-one correspondence between A and B. Okay, what's a one-to-one correspondence? It means that there is a function we can make from A to B so that every element of A maps to an element of B, and every element of B is mapped to from an element of A. And it's a unique one-to-one mapping. In other words, if I have my set A over here and my set B over here, and I have points like this and I have points like this, I can define a function which maps each thing in A to something in B. Okay, there's a nice one-to-one correspondence. So to every element in A, there corresponds an element of B, and to every element in B, there corresponds an element in A. And if that's the case, then I say they have the same cardinality. Now, for finite sets, this is exactly what we would expect, because if I have an extra element over here, I cannot find this one-to-one mapping from A to B. They don't have the same cardinality. If I have extra elements in B, you know, maybe I could map that point to this one. But I've got this extra point sitting over here. They don't have the same cardinality. This will somewhat relate to Riemann sums, to answer a chat question. Yeah, it's very much all the same kind of ball of wax. All right, so cardinality of potentially infinite sets. We don't know what this is, but we know if two things have the same cardinality. There's a one-to-one mapping between them. All right, so here's our change of gears. I like to do strange things on Fridays, and it's Friday, and we've got 25 minutes left in class. So let's do some strange stuff. So I'm going to tell you a story. This story is partially true and partially made up. I'll let you figure out which parts are which. The story is about a mathematician named David Hilbert. Real mathematician. Giant in the field. Late 1800s, early 1900s. Did a lot of groundbreaking work. Trained lots of mathematicians for the coming years. And one of his more famous claims to fame was in the beginning of the 1900s, he posed a set of problems. They're just called Hilbert's problems now. A set of problems that he thought mathematicians should work on over the next 100 years. These are problems that he thought would help develop the field and move things in a productive direction. And so, you know, you'll find entire conferences dedicated to Hilbert's 13th problem or Hilbert's 23rd problem. People will spend their lives working on one of these problems. So that's David Hilbert. All right, so this is the story of Hilbert's Hotel. So the story is that David Hilbert, you know, after posing his problems in the beginning of the 1900s and training more mathematicians, he got bored with mathematics and he decided to retire and he opened a hotel. And this was called Hilbert's Hotel. And it was, you know, a little town in Switzerland, and on one side of town there was this hotel run by David Hilbert. And it was just something he wanted to do in his retirement, you know, take a break from all the conferences and publications and everything and just, you know, run a bed and breakfast. So Hilbert's Hotel opens up. And man, the first day it opens, there's this huge line in the parking lot because this is David Hilbert, the famous mathematician, right? Everybody wants to say, I stayed at Hilbert's Hotel. So all the rooms are sold out. Most of the people in the parking lot, they have to go home. They don't get a room. All right, come back tomorrow. Well, you know, next day there's another big crowd, and this happens day after day, and Hilbert gets the idea, you know, maybe there's a business model here. So he makes the hotel bigger. He adds another row of rooms behind the first row. And, you know, originally it had like 16 rooms in it. Well, now it's got, you know, 40 rooms. That should be enough, right? So it finishes the renovations, opens up the hotel first night, totally sold out, right? Line out the door, line out the parking lot. Everybody wants to stay at Hilbert's Hotel. All right, so Hilbert's hotel is filled up. Hilbert gets the idea, hey, maybe I should make the hotel bigger. So he expands, he adds more rooms, and no matter how big he makes the hotel is always filled up. So he's a mathematician, he can do very fancy things, so he rolls up his sleeves and he pulls out his chalkboard and he does some calculations and he makes Hilbert's Grand Hotel. And what's grand about Hilbert's Grand Hotel is that it has an infinite number of rooms. Okay, what does this mean? If you start walking down the hall, you see the doorways to the rooms, and they're numbered 1, 2, 3, 4. And as far as you can see, there's just door after door after door. What does it mean to say that this hotel has an infinite number of rooms? It's not that there's a door with an infinity on the front, because infinity is not a number. What it means is that if you think of any positive integer, like, 519, there's a room 519, and there's a room to the right of it also. It's not the last room. There is no last room. That's what it means to say there's an infinite number of rooms. All right, so Hilbert's Grand Hotel, infinite number of rooms. Super, we'll never run out of space now, right? So he opens the hotel and people come in and everybody can find a room, and that's all great. All right, well, it's getting to be Hilbert's birthday, and the people in town, are very happy that he opened this hotel, and they love David Hilbert, and they decide, okay, let's throw a surprise party for him. Let's invite a bunch of people, and we'll have a big party and a cake and a band and all this kind of stuff. Awesome idea. Okay, so they start sending out invitations to all the people who have worked with Hilbert and all the people who know him and have read his papers and so on and so forth. And so there's going to be a lot of people coming to the hotel. Now, it's still, just people on planet Earth, so it's smaller than, a few billion. No problem, infinite number of rooms. Well, it turns out they were on the phone inviting people to this party, and one of them made a call to a physics lab in Zurich, and the people in this lab were working on the theory of parallel universes, and had actually opened up a portal to not just one, but an infinite number of parallel universes. And the person who took the phone call said, "What? A birthday party for David Hilbert? That sounds great. When is it?" "July 23rd. Okay. And it's at such and such? Okay. Yeah, great. I'll be there." Well, while this person was saying this out loud, they had this portal open to an infinite number of parallel universes, and an infinite number of civilizations heard about this party. And most of them said, "Oh, cool, free cake and a band, let's go." So now we have an infinite number of guests coming to Hilbert's Grand Hotel. Well, this infinite number of guests shows up, and we can count these guests by the order in which they arrive. There's guest 1, guest 2, guest 3, guest 4, guest 519, guest 520. There's an infinite number of guests. Okay? But it turns out the doorkeeper at the front of the hotel, the head clerk, can find a room for each guest. We have an infinite number of guests, but we also have an infinite number of rooms. All right? So actually the hotel does end up full. Because, in parallel from all these parallel universes, an infinite number of guests arrive, and each one is put in a room. And it works out perfectly, right? When the last key is handed out, well, there is no last key, but when everybody is checked in, everybody's in a room, all the rooms are full, no empty rooms, no guest without a room. It's a perfect one-to-one mapping between guests, guest 1, guest 2, guest 3, and rooms. In mathematical terms, the cardinality of the set of guests is exactly the same as the cardinality of the set of rooms. There's this perfect one-to-one correspondence between guests and rooms. This is great. Party's going on, people are eating cake, the band is awesome, everyone's having a good time. except for this poor graduate student of David Hilbert's whose car broke down on the way to the hotel. And it broke down in the middle of nowhere. He managed to walk to a town with a garage, but you know, the garage was at the owner was at the party, so he had to call the owner back and so on. And they started working on his car, and they said it'll be a few hours. So a few hours later, it's about, 11 o'clock at night, and the graduate student's car is fixed, and they drive into town, and they go to the front desk, and they say, I got here late, but I would really like a hotel room, please. Can you fit me in? And the clerk says, no problem, give me a second, and fumbles around under the desk, and then hands the person a key and says, here's your room, enjoy your stay at the hotel. So yeah, how do you fit one extra person into the room when every room is full to begin with? And you're not Thanos. Yeah, so somebody said it in chat, right? Move everybody down one room. So you have a little button under the counter that lights up a sign in the guests' rooms, and it says, pardon the inconvenience, please move down one door. And everybody gets up and moves down one room, and the new guest can go in room 1. So even though the hotel was completely filled, you could still add one more person to it. Okay, that's part of the nature of infinity. That's part of why it's not an integer, because if this was a billion rooms and every room was filled, you could not add one more person to it. But with an infinite number of rooms, even though every room is occupied, you can still add one more person. And so in math speak, the cardinality of the set of integers is also the same as the cardinality of the set of integers union, some new guest. We feel like this has one more thing in it than that because, there's no letter G in this set over here. There is a letter G in this set, but their cardinality is exactly the same. Alright, well that worked out pretty well. And if another guest shows up late, right, you can do the same thing. And if a party of 10 guests shows up late, you can do the same thing. You can have everybody move down 10 times, and then you can put 10 new people in. Okay, well, it gets to be about midnight, and it turns out that Hilbert had a smaller hotel across town, and a bunch of people thought that's where the party was going to be. And so there were an infinite number of guests on the other side of town, and they suddenly hear the music and they say, hey, we're at the wrong hotel. So now an infinite number of guests shows up and say, we would like rooms at the hotel. Do you have space for us? And the clerk says, yeah, no problem. Hold on a second. Fiddles around on the desk, hands out a set of keys. Here you go, enjoy your stay. So how do you fit an infinite number of guests into the hotel without having to move everybody down an infinite number of times? Lots of good answers, including one which is the one I was hoping for. Have everybody move to the room number that's twice their current room number. Have guest 1 move to room 2. Have guest 2 move to room 4. Have guest 3 move to room 6. Each guest only moves once. Each guest only moves a finite distance down the hall. But now you're left with an infinite number of empty rooms, all the odd numbers. And you can fit an infinite number of guests in there. So if we take 2 infinite sets, each which is as big as the integers, and we take their union, we should get something twice as big, but we don't. We get something with exactly the same number of things as our original set. And that's potentially a little weird. Alright, now here comes Dr. Blauman. Dr. Blauman had a hotel on the other side of town. He was one of the arch nemesis of David Hilbert. So he had Blauman's really grand hotel. And Dr. Blauman's hotel was even bigger than Hilbert's. he had room numbers with real numbers on them. And the largest room number is 10, and the smallest room number is 1. But for any real number in between 1 and 10, there's a door with that number on it. And the guests at Dr. Blauman's hotel decide to come to Hilbert's party, and they all show up at the front gate, and they say, hey, we'd like rooms, can you let us in? And the front desk clerk says, sorry, I don't have room for all of you. And the reason is the cardinality of the reals is fundamentally bigger than the cardinality of the integers. There is no one-to-one mapping between the integers and the reals. We can prove that. We'll prove it next week. We can use something called a diagonalization argument and show that there's no one-to-one mapping between the integers and the reals. They're both infinite sets, but this is somehow a bigger infinite set. Alright, so think about that. We're going to finish this up by talking about how big these infinities are. So lots of things have the same cardinality as the integers. Set of prime numbers, the set of positive numbers, the set of even numbers, the set of rational numbers all have the same cardinality as the set of integers. And so we have a symbol for this. This is called Aleph naught. I never know how to spell naught. Aleph 0. The real numbers has bigger cardinality. Okay, Aleph naught is the cardinality of the smallest infinite set. The next largest infinite set has cardinality Aleph 1. So here's an interesting question. Is there a set S such that the cardinality of S is bigger than the cardinality of the integers, and the cardinality of the reals is bigger than the cardinality of S? In other words, is it possible that the reals are bigger than some set S, which is also bigger than the integers? And this is an interesting question. Is there an infinite set that's bigger than the integers but smaller than the reals in this sense of cardinality? And there's a famous theorem called the continuum hypothesis. Or CH. And the continuum hypothesis says no. There is no set in between here. If you have an infinite set bigger than the integers, it's at least as big as the reals. It could be bigger than the reals. But there's nothing just smaller than that, but bigger than that. And it's an interesting theoretical question. So one person says their gut instinct is no, but I'm not sure. So yeah, good job on the gut. So we don't actually know the answer to this. So how many people think the answer is yes? So a set that's 0.51, 1.5, etc. is going to be the same as Z. And we can prove that. We got a few people who think the answer is yes. How many people think the answer is no? Got one hand. A lot of people don't want to vote. Got two hands. Got more hands. Cool. It's an interesting question. It's one that was studied for a long time. And in studying this question, people came up with a startling realization. They discovered that it was absolutely impossible to find a set that would fit in between here and here. But it was also impossible to prove that you could not find such a set. What people were able to prove was that CH can never be proven and can never be disproven. It's something which is called undecidable. And using rigorous proof techniques, you can prove that this hypothesis cannot be proven and cannot be disproven. The truth or falseness of this hypothesis is outside the grasp of mathematics. It's formally undecidable. And that's a little disturbing, because you make a mathematical system, it's your mathematical system, it's your rules, you should be able to prove or disprove everything, or at the very least, everything should at least be either true or false. CH is neither true nor false. It's undecidable. Alright, so that's your Friday paradox to go into the weekend with. We'll come back to this from time to time. It's not a major theme of the course, but I do want to look at proving that R is bigger than Z. We'll probably do that sometime next week, because that's a powerful argument. And we'll look at other things that are formally undecidable, and we'll look at something called Russell's paradox. And then we'll round out set theory, and we'll start talking about logic and propositional calculus and proofs next week. All right. Have a great weekend. I'll be in office hours from 2 to 3. If I don't see you then, I will catch you next week. Thanks.